in the last class we seen about the basic test bench for combinational circuit. No, so like today I want to explain about the some more programs related to what we call. Today I want to explain about the program. Did you try with the ripple carry half full adder? Full adder you tried? Full adder of subtractor, the programming part. Okay. Okay. Today I will explain you about this what we call carry look adder, programming part of carry look adder and test bench. Okay, and I will try to execute in Vivado as well as first assembly. Okay, so this is carry look adder. Okay, so carry look adder. So my screen is visible. Okay, yeah. So this is my carry look adder. So here this is my carry look adder. So this will start from module carry look adder. So how many inputs are there? 4 inputs are there. Input 3 down to 0. So I'm using a vector 3 down to 0 a comma b. Input C in and input is C in. This is 1 bit only. And output 3 down to 0 sum and output C out. Okay. So sum is output and C out is also output. Okay. And I'm initializing that wire 3 down to 0 CI. Okay. This I'm using initializing wire COT 3 down to 0. As we discussed in the carry look adder, okay, C0 equal to what? C in, no? So assign Ci of 0 equal to Cin, okay, C0 equal to Cin, and assign Ci of 1, okay, C1 equal to what? There is like in carry look adder, you have generate and propagate, okay. So that is what is generate, generate equal to, we already seen, no? Like G naught and so generate equal to A naught, B naught, and propagate equal to A naught XR B naught. Okay. So C1 I can write as what? G naught plus P naught C naught. So that is G naught equal to what? A naught B naught plus P naught equal to A naught XR B naught into C naught and C naught. Okay. So that expression only I am writing. So that is CA of 1 equal to A naught and B naught. Okay. Or A naught XR B naught and CA of naught. Okay, CA of 0. Okay, this only I'm writing. Okay, that is nothing but CA of 1. Okay, this is nothing but CA of 1. And next, CA of 2 equal to what? CA of 2 equal to C2 equal to what you will get? G1 plus P1 C1. Okay, G1 plus C1 C1. And after that, if you substitute G1 equal to A1 B1 and P1 equal to A1 XOR B1. Again, if you P1 equal to this value, you need to substitute. Okay, C1. Here in this C1, you need to substitute. After that, you will get the expression A1 XOR B1 and A naught B naught, A naught XOR B naught, and C naught. Okay, this is CA of 2. Okay, similarly, CA of 3 equal to what? CA of C3 equal to G2 plus P2 and C2. Okay, so that means GT equal to yeah, GT equal to what? GT equal to P2, C3 equal to G2 plus P2 C2, G2 equal to A2 B2, and P2 equal to A2 XR B2 and C2. Again, P2 you substitute. Okay, what is P2 in here? You got the expression. No? That if you substitute, you will get this expression. Okay, so this whole expression you substitute. Assign CA of 3 equal to A2 and B2 or A2 XR B2 and A1 and B1 or A1 XR B1 and A0 and B0 or A0 XR B0 and CA of 0. Okay, this is my expression. Similarly, Cout equal to what? Cout equal to C4. That is C4. C4 equal to J3 plus P3 C3. Okay, and A3 B3, P3 equal to A3 XOR B3, or otherwise P3. Here you got the expression. No, this if you substitute, you will get this expression A3 B3, A3 XOR B3, and A2 B2, or A2 XOR B2, and A1 B1, or A1 XOR B1, A0 B0 plus A0 B0 and C0. Okay. So assign C out equal to that value is substitute. Okay. After that, at last assign is equal to what? A XOR B XOR CL N and 1. Okay. So this is my what we call carry look adder. Okay. So for this I need to write the test bench also. See here. This is my test bench module CLA TB. So whatever the input variables are there that I need to initialize with range data type. Okay, input are nothing but 3 down to 0 A comma B, and output are nothing but C input, and output range C is input, and outputs I need to initialize with range data type. Okay, and next. So I need to instantiate. Okay, what is my design name? CLA adder and instance name CLA. So I'm using what they means connection by position, connection by position with order list, connection by position with the order list. Okay, so this is nothing but connection by position with order list. Okay, so that means however I'm initializing the order of input and output, that same order I'm using here. Okay, and assign add equal to cout comma s. I'm using concatenation operator cout comma s. Initial begin. Dollar monitor is nothing but one system task. Okay, if there any change in the input, it will get change in the output. It will display the change in the output. Okay, A equal to percentage B, this is format specifier. B equal to percentage B, and C in equal to percentage B, and sum equal to percentage B, C out equal to percentage B, and add equal to percentage D. That is a decimal. B means binary, comma A, comma B, comma C in, S and C out, and add. Okay, I am giving the test cases. Okay, A equal to 1, B equal to 0, and C in equal to 0. After 3 time units, I am giving other values. After 3 time units, I am giving some hexadecimal values. After 3 units, I am using some these values. Okay, so this I wrote in the Xilinx Vivado. First, what is the CLA? No, so CLA. I want to see this code. Okay, to see this code, I need to make this as a top module. CLA I need to make as top module. Just elaborate the design. I want to see the hardware. Okay, how the CLA will look like. Carry look at it. Okay. So I think in the digital I told you like why you are going for a carry look at it. There is a in the ripple carry adder there is a propagation delay. Okay, that means in order to propagate the last carry, so first carry should propagate, second carry, third carry, like that. So that's why you are going for carry look at adder. That is the output of the carry is depending only on the first carry. It is nowhere depending on the previous carry, so that we can increase the speed of the addition. Okay, so that's why we are using the carry look at adder. Yeah, see, this is my hardware. This is my hardware of carry look at adder. Okay, carry look at adder. And coming to the simulation, run behavioral simulation. Yeah, see here, I can fit to page. Okay, so expand this just to fit to page. Yeah, fit to page. Here, 5 plus carry look at adder. No? Here if you see to page. Okay. This 5 plus 3 means sum you are getting 9. 5 plus 3 is sum you are getting 9. Okay. Cn is what? Cn is 1. Okay. See here. So that means 5 plus 3 plus 1. How much you are getting? 9. No? So 9 means you are getting in terms of binary. Okay. Binary means what? My 9. So sum you need to see. So 1001. This is nothing but 1001. This is my 9. Okay. So it is adding sum. So in the test bench, what is given? Carry look at a test bench. No? So 5 plus 3 it is executing only. Okay. What I will do in this test bench, yeah, 1 second. In test bench, I not initialize this. Otherwise, 1 second. This is Adder-Subtractor. PB. PB. I'm giving the this time is 10 minutes. Okay, 10 minutes. I'm giving. Okay, you just save this and relaunch the simulation. Yeah, I want to see the simulation. Set to page. Okay. Just zoom this or zoom in. Okay, zoom this. Set to page. Zoom this. Yes. Yeah, see here. So just zoom this. Zoom this. Zoom this. Okay. Zoom this. Yeah, so here when it is 1 plus 0. So in the test bench, what I gave CLA carry located 1 plus 0 means what? 1 and A is 1, B is 0, and the C input is 0. Okay. So in the 1 plus 0 and C is 0. What is sum? 1 you are getting. Okay. See here. And just that yellow line is there, no? Yellow color. You bring it to this side. Hit the page. This side. Okay. This side you bring. And so zoom this. Zoom in. Yeah. You zoom in. Okay. Yeah. See here. So if you place yellow line, this one, okay. So if you place yellow line, what happens? So yeah. So here 1 plus 0, 1 plus 0 means what? 1 plus 0 is you are getting 0, 0, 0, okay. And if you place here, if you drag this, 2 plus 4, 2 plus 4 plus carry input is 1. Carry input is 1 means what? You are getting 7. 7 means in sum also you are getting 0, triple 1. Okay, 0, triple 1. Okay, and next, so in the test bench, next after 10 time minutes, so every period is 10 time minutes. Here B plus 6 plus 1. Okay, B plus 6 plus 1 is how much? Actually, B is how much? 11. 11 plus 11 plus 6. 11 plus 6, 17. 17 plus 17 plus 17 plus 1, 18. Okay, 18 means 18 means what? You need to get carry out is 1. Okay, actually the value is 18. If you convert into binary, you are getting 1 triple 0 1. Okay, so in this case, so in these two cases, you are not getting carry out. Okay, carry out equal to 0 only. Okay, in this case, you are getting what? Carry out equal to 1. Okay, carry out equal to 1. Why? Because my number is what? My number is a 0, 0. So 1 triple 0 1. Okay, so triple 0 1 is 4 bit only. That is given to sum and carry out equal to 1. Okay, that is 18 you are getting. Okay, so that is nothing but 18 you are getting. Okay, 18 if you are converting to hexadecimal, that is what 11. Okay, 11. Okay, you are getting 11. So next is not add. Here you see this one. Sum. Sum is nothing but 1. Sum is 1 and carry out is 1. Okay, carry out is 1. And next 5 plus 3 means what? 5 plus 3 plus 1. Carry out is 1. So here you are getting 8 plus 1. So this is 9. 9 you are getting. Okay, 9 means what? Sum equal to 1001. 1001. Okay, so like this you can see. Okay, and so I'm closing this. So I'm closing the elaborated design. Just ripple carry adder will see. Ripple carry adder. Okay, not ripple carry adder. Adder-Subtractor. Okay, Adder-Subtractor. I told you in the digital, that is Adder-Subtractor. First you need to write the program for full adder. Okay, how to write the program? Module full adder. Input A comma B comma C in, output sum comma C out, and you need to initialize the input and output. I am using a continuous assignment statement, that is assign sum equal to what? A XOR B XOR C in, and assign C out equal to A and B or B and C or C and A and C in, and end module. Okay, this is my full adder circuit. And coming to the ripple carry adder, so first module, what is my module name? Ripple underscore carry underscore adder. Input 3 down to 0, A comma B. And there is a control signal. Okay, so control signal, there I explained, you remember or not. Suppose control signal is given to the B, okay, with the XOR operation. Suppose B XOR 0 means what? B XOR 0 equal to, you are getting B only, okay, it will do addition operation. When control signal becomes 1, B XOR 1 equal to what? B bar you are getting. So B bar means in that situation it is acting as a subtractor. It will do 2's complement subtraction. Okay. So that is nothing but control, input control, and output 3 down to 0 sum comma C out. While 3 down to 0 BC, this you take BC. Okay. This is the intermediate variable. So next assign BC of 0 equal to what? B of 0 and XOR of control. Okay. That control. If control equal to 0, it will do addition operation. When control equal to 1, it will do subtraction operation. Okay. Assign BC of 1 equal to B of 1 XOR control. Assign B of 2 equal to BC of 2 equal to B of 2 under XOR control. And assign BC of 3 equal to B of 3 under XOR control. Okay. And after writing this, you need to instantiate. Okay. How many times here adder-subtractor consists of how many full adders? 4 full adders. No? So that 4 full adders you need to instantiate. Okay. I'm instantiating connection by position. So full adder FA0. So what are the inputs? A of 0, BC of 0, control, S of 0, C out of 0. Okay. This is for one full adder. And next full adder FA1. One input is nothing but A of 1, BC of 1. C out of 0 is the input for this full adder. Okay. C out of 0 and S of 1, C out of 1. Okay. Again, full adder FA2, A of 2, BC of 2, C out of 1, S of 2, C of 2. So this carry out will be the input for this full adder. Okay. And similarly, full adder FA3 equal to A of 3, BC of 3, C out of 2, S3, and C out of 3. Okay, I need to instantiate. Okay, every time I can't write for all full adders. No, first I wrote for all these first one time I wrote full adder, and next time instantiating. How many times means 4 times. Okay, that is nothing but instantiation. And after that, what I need to do? Let us take TB. No, yeah. So module adder-subtractor TB. Whatever the inputs are there, whatever the outputs are there, that I need to initialize with wire data type, wire 3 down to 0 S comma C out, and whatever the inputs are there, that I need to initialize with reg data type, reg 3 down to 0 A comma B, and there is a control. Okay, control is also output. So that's why this is this is input. Okay, input, and these are inputs. Okay, and I need to instantiate connection by name, connection by position with order list, connection by position with order list. Okay, order list. Like this, you need to instantiate. Okay, after instantiation, so how you initialize the inputs and outputs with the same order, you need to instantiate. That is nothing but connection by position with the order list. Okay, and initial begin. Dollar monitor is a system task. If there is any change in the inputs, then there is a change in the, it will display the outputs. Okay. So control percentage B, A percentage B, B percentage B, some percentage B, and C out, that is percentage B, control A, B, S, and C out. Okay. First control equal to 0. I told you, no, when control equal to 0, it will do which operation? It will act as adder. Okay. RCA, ripple carry adder. RCA. Okay, ripple carry adder. When control equal to 1, okay, it will act as subtractor. Okay, parallel subtractor. So parallel subtractor. Okay, it will act as a ripple carry adder or parallel adder. Okay, 1 second. 1 second. Okay. Okay. 1 second. No, I'll open this. Okay. Control equal to 4-bit adder-subtractor. 4-bit adder-subtractor. Adder-subtractor TB. Okay. Yeah, this one. Yeah. So you see. So when control equal to 1, it is acting as a subtractor. I am giving some text cases. Okay. So in the adder also I am giving some text cases. A equal to b to and b equal to 4, a equal to 6, b equal to 3, a equal to 3. And control equal to 1 also I am giving some test cases. Okay. So a equal to 1, b equal to 0, and after 3 time units I am giving a equal to 2, b equal to 1, and 9 and 5, 5 and 3, and after 3 time unit dollar finish. So finish the simulation and model. Okay. So this I am executing in the Xilinx Vivado. First, I want to see the design. Right click, set as top, set as top. Okay. So previously in the TCL console also you got no. In the I told you dollar monitor. So that means 0 plus 1 equal to sum is 0 and carry sum is 1, carry is 0, and add equal to what 1. Okay. And this is 2 plus 4. 2 plus 4 plus 1, 7. 7, add is 7. Okay. And this is what B. B means what? 11 plus 6, 17. 17 means actually this is sum is 0, 0, 1, and 1 is the C out. Okay. And this is 5. 5 means what? 5 plus 3 plus 1, 9. 9 sum is 1, 0, 0, 1, and C out equal to 0 and add equal to 9. Okay. So this is the previous, you can see the TCL console. Okay. So I made this as a top module. If you want to see the design, so elaborated design. Yeah, this is my hardware. Okay. 4 full adders are there. Okay. And I told you, so the one bit is what A3 down to 0. Another bit is B3 down to 0. These are 4 bits. And outputs are C3 down to 0 and some 3 down to 0. And there is a control. Okay. So control is 0 means it is given through the XOR gate. Okay. XOR gate, and it is given to B input. Okay. It is given to B input. And when control equal to 0, it will be act as what? Normal parallel adder, that is ripple carry adder. Okay. When control equal to 1, it is acting as a parallel subtractor. Okay. Here itself, I covered both concepts. That is nothing but ripple carry adder as well as parallel subtractor. Okay. Parallel adder and parallel subtractor. Okay. This is the tool will converting into hardware. Okay. Tool is converting into whatever the program you wrote. Tool is converting into hardware. Okay. And coming to the simulation, run behavior simulation. So if you see, yeah, 1 second, yeah, fit to page. It is Adder-Subtractor, no? Yeah, 1 second. Okay, I'm closing this. Okay. Yeah, this I need to make a stop module. Okay, in the simulation also, Adder-Subtractor I need to make a stop module. Now run the simulation. Okay, if you run the simulation, here you see, just a fit to page. Yeah, I got control. Okay, so just bring this one to this side. Yeah. So till here the control equal to what? Control equal to 0. So till here it will do addition operation. Okay. So what is my inputs? 1 plus 0. 1 plus 0 means what? So A is 1 and B is 0. 1 plus 0 is sum 0, carry 0. Okay. And similarly, here you see. So we drag here. 2 plus 4. 2 plus 4 is 6. Okay. Sum is 6. So internally it will display in terms of binary also. Okay, 0110. Which is nothing but 0110. Okay, and here you will get carry out. So I'm interested to see the sum only. And here you see. So 6 plus 6. 1 second. 6 plus 3. 6 plus 3. And carry input. So control is 0. That means it will do the addition operation only. 6 6 plus 3 means what? It will do 9. So sum is 9. And carry out is 0 only. Okay, carry out is 0 only. Okay, and next, so carry out is 0 only. And next, here it will do subtraction. So what is A? A is 1 and B is 0. 1 minus 0 means you are getting sum equal to what? 1. Sum equal to 1. Okay, and here you see. So A is 2. 2 minus 1. 1 only you are getting. 9 minus 5. 9 minus 5 means 4 you are getting. And 5 minus 3. 2 you are getting. Okay, like this you will get. Okay. So like this you can simulate. Okay, fit to page. Suppose like the same thing I can execute in PastaSim also. So how to execute means here you see. Just to open this PastaSim. So wherever that these programs are there, so you have 4-bit Adder-Subtractor and CLA, no? 4-bit Adder-Subtractor. Just 4-bit Adder-Subtractor is there, no? 4-bit Adder-Subtractor. Yeah, 1 second. This one, just this path, just copy this. Okay. Yeah. CD. Uh, so CD space. Flower bracket. Go to that path. Okay. ls. Okay. These are there. Vlog dot. First, yeah, this one I want to see. Okay. Space. Or otherwise, you want to go to there, no? CD flower bracket. I want to go into this folder. Yeah. To go into this folder. Yeah. Copy this and paste in this. Okay. So what is my do file? This do file is there. Okay. Run file is there. Okay. The run I want to execute. Okay. So do space run dot do. This will execute. Some error is coming. Okay. 1 second. Actually CLA if I go, run file is there. Copy this. Yeah, first you need to create the work function, no? Okay, 1 second. You need to create the work function. Okay, work function you need to create. Okay, quit sim, quit minus sim. Okay, so in do file what is there? In run file. Okay, will work is there. Okay, first I need to create the work function. Okay, quit I quit sim. Passed. Yes. Once again I'm opening. Just cd space go to that file CLA. Okay. So enter VLabel work vmap work do space run dot do. Okay. Vlog dot 4-bit Adder-Subtractor is there, no? 4-bit Adder-Subtractor plus ASIC. Vlog dot plus ASIC. Getting errors. Okay. the CE.